So we have been discussing about the overall functionality of an optomechatronic systems. So we have been discussing about the different function of an optomechatronic system. So the various functions which are involved using a sensing, optical scanning, a motion control, an optical actuator with visual inspection, a three-dimensional shape construction, a laser material processing, an optical pattern recognition, and a real monitoring control. So we have also discussed about an optomechatronic system, how it is used in the case of a robotic platform, in which we have been discussing about the different components and the subcomponents which are involved in the case of an optomechatronic system. Like so we have discussed about the image acquisition, the different domain which includes the light source, the illumination angle, the image acquisition, the image processing, and then the overall a domain. So in the overall domain, how the images are captured. And then we also had a discussion about a simple system where a kind of piezoelectric actuator integrated with CCD camera and a tube and a locomotion propulsion system is deployed for a kind of a surveillance or for a kind of capturing the image at the localized locations. So there are wide varieties. So we also had a discussion about the MEMS-based optical sensor, the overall application of the optical sensor, about the optical-based sensor and its application towards displacement measurement. There are different techniques which are being deployed for optical-based system, optical sensors, which are being categorized based on their working principle and their application. So the main types includes the triangulation based sensor, then interferometer displacement sensors, and a confocal sensor, a time of flight sensor, and an optical sensor. So we had gone in detail about the different categories of this optical based sensor, and like one is a kind of a triangulation based sensor, how these triangulation based sensors are deployed for micro robotic related applications, and interferometric displacement sensors, a confocal sensor, a time of flight sensor, and then now we will discuss about the shadow projection sensor. So some of the key components which are involved are a collimating lens. So this is a laser diode, collimating lens, so there are two components are there. One is a kind of a light source, and this is a CCD image sensor and a receiver. So it comprised of a small region with a band pass filter, and the shadow coming out of it is projected on a CCD array. So let us consider an object is moving. and this is the projected shadow, and this is the moving object. So, this is the overall construction of a working principle of a shadow projection sensor. So, in the earlier cases, we were directly capturing the image and we were trying to sense the image from the front reflection. This is a kind of an arrangement where we are trying to capture the shadow, and these shadows are used for visualization of a dynamic particle. So, when we observe the overall working principle of this shadow projection sensor, a collimated light beam is projected on a CCD sensor receiver. So, any object which is interrupting the beam projects a shadow on the receiver that can be used as a means for measuring the displacement of the object passing through the beam. So, there are wide varieties of configurations are there. These kind of shadow projection sensors also can be used for collecting the transmitted light through a fluidic channel. If we have a construction, this is a kind of a fluidic channel, and the object is moving, and this is the shadow projection sensor. This is a waveguide, which is a guided light source. And we have the moving object. So, here, like as far as in this shadow projection is concerned, let us consider there are 4 quadrants are there. So, this 4 quadrants collects the transmitted light through the fluidic channel. So, when objects passes in the tiny fluidic channel, they mask the light partially or completely, thus modifying the transmitted signal. By analyzing the signal collected on such kind of on the shadow projection sensor, one can infer some information about the object passing in the channel. The channel to guide the object through the detector can be made small as few tens of micron, which the waveguide itself has a size of few micron. So, now in this particular case, let us consider we have discussed about this magnetic micromanipulation. So, when a series of magnetic micromanipulated actuators or microrobots move through this system, so we can easily observe the complete shadow projected region using this particular technique. In fact, in that particular module, when we are discussing this movement of this magnetic micromanipulated robot, so we could see that there is a kind of a features which are being observed. So, these features can also be visualized using this particular system. Okay. Now, let us discuss about the next configuration. So, the next configuration is called as an optical encoders. These optical encoders are efficiently used for measuring the RPM or measuring the angular position. So, if we see the overall construction of it, these optical encoders comprises of a light source. In order to focus the light, we are using a lens. Then there is a kind of a fixed slit which is available and a photosensor which is available. This is a kind of a code wheel for which the RPM of this code wheel needs to be measured using this system. So, as far as these optical encoders are concerned, these optical encoders are motion sensing devices that convert a mechanical motion into an electrical signal using a light to detect the position or motion. They are widely used in applications requiring high precision and reliability such as robotic, CNC machines, motor control systems, etc. If we closely observe the working principle of it, the light source shines through the encoder disk, which has a pattern of opaque and transparent segment. As the disk rotates, the light passing through the transparent segment is detected by the photodetector, generating electrical signal. So, the signals are processed to determine the position, speed and direction of the encoder of the shaft. Now, like as far as this optical encoder perspective point of view, so these optical encoders are classified into two. One is called as an absolute encoders and the other one is called as a incremental encoders. As far as these absolute encoders are concerned, let us consider, so we have a fixed slit. This slit is in this form with a particular slots which are available, and then there is a laser source is there and a detector which is there. So, now what is happening is light is passing through this. If I need to measure the angle within a kind of a single rotation, then such kind of absolute encoders can be employed. However, if I want to go for a multiple rotation, for example, if I am connecting it, so if I want to know the rotation of a servo motor, then an incremental encoders can be deployed. In case if I want to know the rotation or the RPM or the angular value theta with reference to a stepper motor, then an absolute encoders can be efficiently deployed. Okay. So, with reference to the overall construction, it is an highly compact system, and as far as the particular signal processing perspective point of view, it does not require any kind of complicated signal processing. So, it is a kind of a go no go gauge kind of process, so which can be helpful for us to understand the overall RPM which is being generated over here. Now, as far as an application perspective point of view, like of these optical encoders or such kind of optical sensors, it is widely used for industrial automation and robotics, basically positioning a robotic arm with high accuracy and detecting the product misalignment. Next, it has a potential application towards semiconductor manufacturing, especially wherever we are looking for a kind of a micro manipulation. Measuring the wafer thickness and position can be easily monitored using this. So, this kind of systems are efficiently used or deployed for aligning a photo mask for a lithography process. Then, with reference to precision engineering and metrology perspective point of view, it is used for measuring surface roughness of a machine part, checking the flatness and alignment of the component. With reference to automotive industry perspective point of view, it is highly used for wheel alignment and suspension testing, measuring a brake disc thickness, and a medical application point of view, it is used for analyzing the eye movement for medical diagnostics and high precision position in surgical robots. So, these are some of the key applications where such kind of optical systems can be employed. Now, let us discuss about the next concept, which is developing a sensor or analyzing a sensor based on the light intensity model. So, as far as a light intensity model is concerned, a sensor based on light intensity module are used to detect the change in the environment as well as the change in the by varying the environment by varying the light intensity. These sensors are common in fiber optic systems and are categorized based on their operating principle as well as based on their applications. Now, in this aspect, as far as this light intensity modulation is concerned, these light intensity modulation systems are based on the intensity of the light is modulated based on the measurement, the quantity being measured. This can be achieved by changing the amplitude or current of the light source, typically a laser diode. In fiber optic sensors, modulation can occur through a mechanism like microbending, evanescent wave coupling, or external perturbations affecting the optical path. So, as far as detection is concerned, the modulated light is detected by a photodetector such as PAN or APD photodiodes, which converts the optical power variation into a corresponding electrical current or voltage variation. So, the detected signal is then processed to determine the change in the measurement. So, as far as in this particular case is concerned, signal processing is considered to be one of the key characteristics which takes up a shape. So, the signal processing, as far as the signal processing is concerned, the electrical signal generated by the photodetector is often weak and may require a kind of an amplification. So, the amplified signal is further processed to extract a kind of a useful information such as intensity or wavelength of light, which corresponds to the measurement quantity. So, in this particular case, in most of these modulations, these modulations can be useful to measure the pressure, strain or rotation. The light in through the feedback and light out through the feedback can be efficiently monitored. So, as far as this amplitude modulation is concerned, there are different types of amplitude modulation techniques with reference to light. So, different types of modulation techniques with reference to light. One is called as amplitude modulation, another one is called as pulse modulation technique, optical intensity modulation, frequency and wavelength modulation, digital intensity modulation technique. So, these are the different configurations of the modulation techniques which are being employed. So, like overall, if you consider this as a signal, so this is a kind of an amplitude modulation and this is a kind of a frequency modulation which exhibits. Now, the role of fiber optics in an intensity modulation basically is a crucial role. It plays a crucial role with reference to an intensity modulation sensor by enabling the transmission and modulation of the light to detect the change in environment. So, in that aspect, we have a light transmission, we have an intensity transmission and a sensor configuration which persists. Now, let us discuss about the light transmission and reflection. So, in the case of light transmission in fiber optic sensor, it involves guiding the light through the optical fiber to detect the change in the environment. So, the light is confined within the fiber core due to the total internal reflection, which occurs because the core has a higher refractive index than the clad. This principle allows the light to travel long distance with a minimal loss. So, with reference to a light source, typically an LED, laser diode or superluminescent diodes that generates the light are used. And the light reflection uses a reflective surface to modulate light intensity. The distance or position of the reflector affects the amount of light reflected by the detector. So, the commonly used in displacement and vibration sensing, where the changes in the reflector position modulates the light intensity. If we look closely observe the overall construction of this optical fiber sensor, so this is a kind of a this is called as a core and this is the clad. So, the complete clad is made out of highly reflective material. So, through the center, the light is made to pass through the core and there is going to be a multiple reflection and the receiver will receive the signal. So, appropriately when there is a bending is employed. So, these bendings or any kind of change in the parameter can be efficiently observed using this particular system. So, like here it is something like this, it is a kind of a tube. So, through this tube we have a light which is passing through it. Any change in the parameter on this tube or any influence of parameter on this tube will impact the receiving end, which is going to be ideally a detector. Now, let us discuss about the intensity modulation. So, as far as this intensity modulation perspective point of view, let us consider like this is a kind of an this is an extended version of an optical fiber in which a core and clad is there. There is going to be a multiple reflection in this particular system. what we are trying to do is we are trying to apply an external force at a particular point. That is, we have an optical fiber. In this optical fiber, we are trying to apply a small pressure on top of it. When we try to apply a small pressure, there is going to be a kind of a multiple reflection which exhibits. This multiple reflection will affect the clad and the core. So when the external force impacts on the clad, there is going to be a kind of a bending which persists, and when the light falls on this clad where there is going to be a bending, this will affect the internal reflection which is passing through it. So like without the external force, already we will be having a reference signal. After applying external force, there will be a change in the light signal. The difference between this reference signal and the light signal will give us the amount of force exerted on the optical fiber. So either it can be a force, in case if I have an optical fiber and if I am going to bend the fiber appropriately, it will have an impact on the intensity system. So this is how an optical fibers can be used as a sensor. So when we try to consider the intensity modulation of it, so when we try to consider the micro bending mechanism, so it involves bending the fiber to create a micro bending losses which modulates the light intensity. So the degree of the bending affects the amount of light transmitted. So used in pressure, vibration and displacement sensing where external forces causes micro bending. Now we also have a kind of a wave coupling mechanism. So this utilizes the evanescent field of light in a single mode fiber to interact with the external medium. So change in the surrounding media modulate the light intensity, and this is ideally used in a kind of a chemical sensing or biosensing, where change in the refractive index of the surrounding medium affect the evanescent of the wave. So we will discuss in detail about this. Now when we try to talk about the optical fiber based sensor configuration, so there are two different sensor configurations are displayed. One set of sensor configuration includes optical fiber on transducer, and the other set of sensor configuration is with reference to a light modulator. Now the sensor use the fiber itself as a sensing element. Change in the fiber properties, example the micro bending including the modulated and the light intensity. The external components modulate the light intensity, for example the reflective intensity modulated sensor such as mirror or reflective surface to modulate light based on the displacement pressure. So the fiber optic sensor can be configured for various applications including the structural monitoring and the biomedical sensing. Many configurations offers highly sensitive to environmental changes, allow for simultaneous measurements of multiple parameters using a single fiber system. Now when we try to look into the advantage of this system, so these light intensity modulated sensors offer several advantages, making it widely used technique for measuring various physical, chemical and environmental parameters. So some of the parameters which basically includes a kind of a high sensitivity, simplicity of detection, immunity to electromagnetic interference, long distance sensing capability and non-contact and non-intrusive type measurements are some of the key advantages in using such kind of sensor configurations. The next we will be discussing about the interferometers for microsensing in the upcoming classes.
This is a Michelson interferometer. So this is a light source, okay, and these are two mirrors, mirror 2 and mirror 1, where we adjust. This is adjustable mirror and this is movable mirror with the help of this micrometer knob, and this mirror can also move with the help of this knob. And this is beam splitter which splits our laser beam. So what happens? So laser beam incident on the beam splitter and it is split in two parts, and after this after reflection from the both the mirror the waves are interfere here, and in front here, what happened in this view. So the light will be splitted with the help of this beam splitter, and these are the two mirrors from where the reflected light wave will interfere, and constructive and destructive interference will be occur. So this time this is constructive interference. So when we move our movable mirror with the with 1/4 wavelength with the help of micrometer NOC, so destructive interference will be occur. So we can see here the maximum of both the wave are opposite sides. So initially distance is d0 between from the beam splitter and the mirror, and when we move mirror by 1/4 of wavelength of the light, the destructive interference will be occur. And when we move our mirror by 1/2 of the wavelength, the constructive interference will be occur. So what happened when interference occur? We saw these fringes. So dark one is because of the destructive interference, and the brighter one is because of the.
Bimorph integrated optical fiber sensor was designed by integrating optical fiber with Bimorph. SMA coating was done on the fiber by placing it on the holder during deposition in thermal evaporation unit, and is rotated at a fixed RPM for ensuring uniform coating all around the fiber. The SMA coated optical fiber appears strained because of its martensite phase retention. This is holder for keeping Kapton polyimide sheet for depositing SMA on it and developing Bimorph using this sheet. The Bimorph developed appears strained because of its martensite phase retention. The curvature and luster is there because of SMA thin film. The thermomechanical actuation of Bimorph can be tested on hot plate. During heating, it expands because of austenite phase, and while cooling, it happens that the phase retention is there. This phase transformation behavior was observed in the window of SMA between 80 to 120 degrees Celsius. This smart actuation of Bimorph has been captured by integrating it with optical fiber using optimal dimensions. Initially, the optical fiber remains in macroband state, and upon heating, Bimorph actuation results in bend release, which increases the optical signal, and this bend again gets retained upon cooling. This real-time actuation of optical signal can be captured on LabVIEW or other signal processing devices and help in smart sensing. Can be integrated with alarm systems or IoT for real-time monitoring of the systems. As an application, we have tested the sensor performance on hydraulic power pack, and real-time temperature monitoring under the influence of pressure and load was done through IoT. This was the location in which the sensor was placed.